Hello, calculus students, seekers of truth. We will continue now our study of logistic functions. Remember, a logistic function eventually will, when we work through the differential equation, it will give us this function right here, where K is the carrying capacity, R is the growth parameter or the growth rate, and C is some generic constant. Okay. And in this example, we have bacteria that grows logistically. The initial population is 3, the carrying capacity is 100, and the growth parameter is 0.2. So in this case, we can write most of our equation. We know that P of T is going to be equal to 100 because that is our carrying capacity, divided by 1 plus some constant e to the negative 0.2 t. Now, we also need to solve for this constant c, and that's not a problem because we know that the initial amount is 3 milligrams. Okay? So that tells me that P of 0 is equal to 3, and so we can set P equal to 3. We can set this equation right here, and we can solve. And we can put in 0 here for t. Okay, I will let you sort through the details yourself, but once we finish with this, we get that c is equal to 97 over 3. Okay. So now our final equation takes on this form. P of t is equal to 100 over 1 plus 97 over 3 e to the negative 0.2 t. So there we go. We have a differential equation that satisfies that's this population. Okay. So actually, I'm sorry. What I've done here is answer part B. I'm sorry. Part A is actually a little bit simpler. Part A is find a differential equation that's satisfied by the population. So part A, let's do that over here. Remember that the derivative with respect to time is equal to the growth rate times P times 1 minus P over the carrying capacity. Okay? So in other words, if I were to solve this equation, this differential equation, I would get this function. So took care of part A, took care of part B. All right, next, when will the population reach 90 milligrams? So that's not hard to solve for. We set 90 equal to our equation. You can certainly do this using a calculator, graphing. I'm going to try to solve it algebraically as much as I can, just so you get some practice. So cross multiply, or multiply both sides by this denominator and divide by 90. So we get 1 plus 97 thirds e to the negative 0.2 t is equal to 100 over 90, or 10 over 9. Okay, we're going to subtract 1. And so 10 ninths minus 9 ninths is 1 ninth. And then multiply by 3 over 97. So this is going to be 1 over 97. One third times 97. Okay. And then take the natural log of both sides. On the left, we get negative 0.2. On the right, we get the natural log of 1 over 3 times 97. And then divide everything by negative 0.2 or multiply by negative 5. And let's see if I can do 3 times 97 in my head. That's 3 times 100. And so that's 300 minus 3. Sorry, minus 9. So that's 291. Okay. And let's Let's see what our calculator tells us. So doing that, I got t is equal to about 28.367 years. All right, next question. When will the population's rate of change start to decrease? Now, this is actually a pretty tough question, so I'm going to save it for the end. I'm going to answer the next question. When will the population reach 200 milligrams? Well, if you see here that the carrying capacity is 100, then the population is never going to reach 200. And so let me explain. If we were to create a graph of this, it would look something like this. Okay? All logistic functions, logistic growth takes that format. If this is the population and this is time, we know that the population will reach 90. So 90 is approximately here. Okay, so, and this is going to be like 28.367. So that's this point right here. And then the carrying capacity, or the limit to growth, this is 100. So when is the population going to reach 200? Well, this line is going to level off here. So we can say never. So that's really nice. Okay. Now the second to last question here, when will the population's rate of change start to decrease? Now this requires a little bit of deeper thinking. So this is like saying, when is dp/dt going to decrease? Okay, so this the rate of change, right? So when is dp/dt going to decrease? And so there's two ways to answer this question. One way is we can look at the second derivative. That comes in very handy. And another way to do this is just to study this function by itself. So if we were to study the graph of this function, what would this look like if we were going to graph the population along the horizontal axis and the derivative? Okay. Note here, this is a very different graph than what we are normally doing. The shape of it is very familiar and common, but the meaning of it is different. We're graphing a function, the output of a function here, against its own derivative. Okay, so p is like the input, and dp/dt is the output. Okay. And so if we treat it this way, you can see that this resembles a quadratic. Okay. If we were to multiply this out, you would get, p prime or dp/dt is equal to some multiple of p minus some multiple of p squared. Okay, so it's going to be a quadratic. Let's solve for the x-intercept. So 0 is equal to 0.2p times 1 minus p over 100. So we get two solutions. P is going to be equal to 0, and 1 minus p over 100 is going to be equal to 0. If we solve this, and so p is going to be equal to 100. This quadratic is going to open downwards because the p squared here, when we distribute this, is going to be negative. So it's going to look like this. Now, I have to point out one minor detail here, is that these points right here, they should actually be zeroed. I mean, they should actually be open rather than closed. And I'll explain that in just a minute. But just to be clear, these should be open. Should be open. Okay? Now, why would they be open? Well, can the population ever actually reach 100, right? Well, we already know that from here, the answer is no. As time goes on, the population gets ever closer to 100, but the population never actually reaches 100. And over here, can the population really be 0? Well, the initial amount is right here, but there's a horizontal asymptote down here as well, so the population never actually reaches 0 either. Now, if you notice here, what's going to happen to the derivative? Well, the derivative is going to increase from this whole, from p equals 0 until this point right here, and then after that the derivative is going to decrease. And so this matches our graph that the the graph is going to be concave up until P reaches a certain value right here. This is its point of inflection. And then the graph is going to be concave down. Okay? And to solve for this point right here, it's not hard at all. It's the average of 0 and 100, so this is 50. Okay? So when P equals 50, when will the population's rate of change start to decrease? Well, it's when P is equal to 50. Right? That's when the rate of change is going to start to decrease. And so I can map this out over here. This point here is going to be equal to 50. Right? And let's work through the algebra, and we want to figure out what's the time as well. Okay, so at what time will that occur? So let's see. We can take our equation that we have formulated up here. We set that equal to 50, and then we solve. So 50 is equal to 100 over 1 plus 97 thirds e to the negative 0.2 t. All right. I'm going to do the algebra quite quick. I highly recommend you slow it down, you work it through yourself, and then compare it to my answer. Okay. But if we do a quick flipping of things, we end up with 97 over 3e to the negative 0.2 is equal to 1. Okay, I'll let you have fun seeing how I got that. So t then is equal to negative 5 times the natural log of 3 over 97. So that gives me an answer of approximately 17.380. In other words, at that time, at this time right here, 17.380, that's when the inflection point is going to occur, and that's when the population of a bacteria is going to go from increasing at an increasing rate to increasing at a decreasing rate. As always, keep working hard. We're going to have one more video here where I explain some of the general concepts with respect to the point of inflection, and then we'll actually see some other work where we're actually going to derive this function. Thank you for watching, and have a wonderful day.